Propellers are characterized by a number of parameters: the diameter, which is the size of the propeller; the pitch, which is the, well, in layman's terms, if you put a propeller in a room full of butter and give it one full revolution, the pitch is the distance that it would move forward. Is a very simple explanation of pitch. The pitch ratio is the pitch made non-dimensional by dividing by the diameter. Typically, pitch ratios vary between 0.6 and 2. Most of the series propellers have a pitch ratio between 0.6 and about 1.6. However, there are some series, particularly the Gorn series and the Gorn Burrell series, they go up to a pitch ratio of 2. The other one is, or the other two, the number of blades typically vary between 2 and 7. 2 you usually find just on yacht propellers, where you can arrange to have the 2 blades vertically in line with the stern post. For most other vessels, it usually ranges between 3 and 7. The blade area ratio, that's the expanded blade area divided by the propeller disc area, typically ranges from 0.25 for yacht propellers up to 1.1. Most commercial propellers, I would say, have a lower limit of about 0.35 or 0.4, up to 1.1, where the blades actually overlap on the propeller. The propeller manufacturer will find that very difficult to cast a propeller with overlapping blades, but they can do it, and it's not a problem. When the propeller is operating behind a vessel, it operates in water of what we call the speed of advance. And the speed of advance is usually less than the speed of the ship through the water, although it can be more. The wake of the propeller, or wake at the propeller, is due to the friction on the hull, and you all know from your fluid mechanics that with a ship moving through the water, it develops a boundary layer as the ship proceeds through the water, which increases in thickness towards the stern of the vessel. And that appears as a slowing of the water flowing past the propeller. There's also the streamline flow as the water is coming in around the stern of the vessel, which again is a slowing of the water around the stern. And then finally, you have the motion of the particles in the wave crests and the troughs, where in the crest of a wave, the particles are moving forward in the same direction as the vessel, and in the trough, they're moving sternwards against the direction of the vessel. That has the application that for high-speed vessels, say operating at a speed length ratio of 2, you have a wavelength of half the length of the vessel, and so you're going to have a trough right at the stern where the propeller is operating. And that means that the water particles there are moving sternwards and actually increasing the speed of advance of the propeller through the water. So as a result, if the wave particles in the trough at the stern are moving faster than the sum of the boundary layer, the friction on the hull, and the streamline flow, you may have the speed of advance greater than the speed of the ship, or if it's not as large as that, if you have a lower speed length ratio, the speed of advance may be less than that of the speed of the ship. So we have two things here. Typically, the wake is measured by the Taylor wake fraction. The Taylor wake fraction is the difference in speeds of the speed of advance and the speed of the ship, made non-dimensional by dividing by the speed of the ship. And so if you rearrange that first equation, you find that the speed of advance is the speed of the ship multiplied by 1 minus the wake fraction, the Taylor wake fraction, or some authorities refer to this as the wake factor, and you have to be careful which one you're actually talking about. The thrust deduction fraction is the thrust of the propeller minus the, that's the open water thrust minus the pull, made non-dimensional by dividing by the thrust. So that from that you can have the pull, which is equal to the total resistance of the ship at that stage, as the thrust or the open water thrust multiplied by 1 minus the thrust deduction fraction or the thrust deduction factor. We call the advance constant, that's J, the speed of advance made non-dimensional by dividing by the diameter of the propeller multiplied by the rate of rotation in revs per second, making it non-dimensional. We have two coefficients, the thrust coefficient, which is non-dimensional, and the torque coefficient, which is non-dimensional. Both of them depend principally on the advance constant and the pitch ratio, and to a lesser extent on the number of blades and the blade area ratio. Much of the data that we have on propellers has been derived from tests of model propellers, and they're usually tested as series. And some of the more useful series are the ones that I've shown on the screen there. For open water propellers, we have the B series, which was originally developed as a result of 3 papers by Professor Lawrence Troost at what was then the Netherlands Ship Model Basin, now called the Maritime Research Institute Netherlands. And they developed the B series and subsequently modified that slightly to what they call the BB series. And the BB series differs from the B series in that it has slightly wider blade tips in order to reduce the incidence of cavitation at the towards the tips. Then there's 2 famous series of papers, the Gaughan series and the Gaughan-Burrell series. Gaughan was actually Burrell's PhD student at the University of Newcastle on Tyne, as it was called then, or just Newcastle University these days. And that series was characterized by segmental sections for the whole lot of the blades, and they were based on oval, elliptical shaped blades. The Gaughan-Burrell series in particular had cavitation data prepared for it. And if you take the 2 series together, the Gaughan series and the Gaughan-Burrell series, it gives you a very wide range of A, pitch ratios, and B, blade area ratios. They're all open water propellers, but it's very useful for high speed type applications, particularly the wide range of pitch ratios going up to 2, and the blade area ratios going up to 1.1. The Newton Raider series was a small series, but again, it's applicable to high-speed type vessels, and the AU series. The nozzle or ducted propellers, MARIN, the Maritime Research Institute Netherlands, has done extensive series of tests on both KA, that's Kaplan-style blades, which are blades which have the tips cut off in a circular arc in order to fit inside a nozzle. And they do both the Kaplan accelerating type nozzles and decelerating type nozzles. An accelerating nozzle is where the diameter of the propeller is less at the operating plane, is less than the intake area of the duct, less than the diameter at the intake of the duct. And a decelerating duct has the diameter of the propeller larger than the diameter of the propeller at greater than the diameter of the intake of the nozzle. And they both have their particular applications. This is what a typical KT and KQ chart looks like, where you can see up at the top, the lines, I don't know if you can see here, these lines up here are the typically 10 KQ values. These lines here are the KT values, and these ones down here are the KTN, or the thrust derived from the nozzle. That is the lift in the forward direction, which is obtained by having the aerofoil shape on the nozzle. And you can see over here on the left, these values at J = 0, that is at the bollard condition, the KTN can be up to half of the value of the total KT for the nozzle and propeller combination. And the proportion decreases as the advanced coefficient increases up here. This is the advanced coefficient going up here. We plot 10 KQ for the torque coefficients because the KQ values are typically a little bit more than 1/10 of the values of the KT. And so you can use the same scale up here, but you plot 10 KQ up here on the vertical axis. Back in 1975, Marin published the first of a set of polynomials for the B series propellers. And the typical polynomial for the B series includes as variables the pitch ratio, the advance constant, the number of blades, and the blade area ratio. And you can see there that the Gorn series and the KCA series, or the Gorn-Burrell series, also has the same basic formulation as the B series. The nozzle propellers have a slightly different formulation. What they do is they only have the pitch ratio and the advance constant as variables, and they are published for separate numbers of blades and blade area ratio combinations. That means that if you have a blade area ratio, for example, which falls between the published polynomials for one blade area ratio and another, you then have to work it out for both and then do an interpolation between the two. The delivered power. The typical units for the maximum continuous rating brake power is usually in kilowatts. But if you deal with engines from either Europe or from Japan, you're going to find other sets of units. And particularly European engines usually measure their power in Federstark, which is the German word for it. From the French manufacturers, it'll be in cheval vapeur, like from Baudouin engines. But both of those are equal to 75 kilogram meters per second, which is 0.7355 kilowatts. Or if you have engines from English Electric or any of the British manufacturers, they're going to be in horsepower, which is 550 foot-pounds per second, or 0.7457 kilowatts. The power that you get delivered to the propeller from the engine that you have installed, you have to derate the engine for tropic conditions, because the engine manufacturer will supply you an engine which is guaranteed to deliver a set power at standard air temperature and pressure conditions. It does not include tropic conditions. So if your engine is going to be operating in the tropics, for example, if you've got a prawn trawler operating in the Gulf of Carpentaria, or you've got Armidale-class patrol boats operating out of Darwin all the time, you will have to derate the engine for tropic conditions. And typically that can be between 5 and 10%, depending on how comfortable you feel with your particular choice. So you multiply it by the tropic efficiency, which say 5 or 10% D rate would give you a tropic efficiency of 95 to 90%. Each engine will then possibly have other things being driven by it, which the engine manufacturer has not allowed for. For example, if you put a steering pump on the back of a diesel engine, the engine manufacturer hasn't allowed for that. So if it's taking a kilowatt, then you need to subtract off this figure, that combined figure, what we call engine-driven auxiliaries. It might be a steering pump, it might be an extra alternator, it might be any of those sorts of things. And then the engine is going to be driving through a gearbox. Now, most gearboxes have a typical loss from the input to the output of 3%. So you would say your gearbox efficiency, that's, oh, I've lost my cursor. Oh, there it is. The gearbox efficiency you would typically say is 97%. And then finally, there's going to be the efficiency or the losses transmitted when the power is transmitted down the shaft. You've got a number of bearings along the line of the shaft. You've got the stern tube, which is typically lubricated either by oil or by seawater itself. There's going to be a stuffing gland there or some form of sealing arrangement. All of these generate losses, so there's going to be an overall shaft efficiency. If you've got engines midships, typically 2 or 3% losses, so 97, 98% overall shaft efficiency. If your engines are aft, typically 1 or 2%, so 90, 98, 99% efficiency. And that's going to be give you a torque at the propeller of 2 pi times the rate of rotation times the torque. Now, when we start talking about design paths, because you've got you have 7 variables, and if you specify any 3 of those, it defines any 4 of those, it defines the propeller completely. So that means that you have factorial 7 divided by factorial 4, which gives you about 834 possible design paths. Now, that's obviously far too many for your average design office to cope with, and you're usually not going to be looking at anywhere near that number of paths. The most common are where the pull is known. That is, you need to, you have the resistance of the vessel at a particular speed. You know what the resistance is, so therefore you know what the pull required from the power is. And you want the engine power required to drive the vessel at that resistance, at that speed. And what you want to do is to minimize that power requirement by changing the diameter and the RPM. The other one that you usually have is the power is known, but you want the pull that is produced by the propeller, and you want to maximize that by changing the diameter and the RPM. And the best is, of course, the large diameter or the largest diameter that you can fit on that vessel, turning as slowly as possible. And diameter is usually one of the limiting factors in the design of any propeller. If you found, for example, that the diameter was, that the best diameter was not the largest that you could fit into the aperture or on a twin screw vessel fit in the location for the propeller to go, it's a good bet that if you change the gearbox reduction and had the propeller turning more slowly, the larger diameter would give you better efficiency. So looking ahead, if we know the power, well, we want the power for a known pull, that means that we know the total resistance and we have all those other things there in the top line. We select from, we select a particular diameter and a speed of rotation. We can calculate all those other things down there. And then what we do is vary the diameter to minimize the total brake power required. And if we have the opportunity, we select diameters lower than the aperture will take, or can be fitted on a twin screw vessel, and see what happens to the brake power required, and see what happens to the rate of rotation. Then if you've got a particular engine installed in a vessel, see what you can do here is work out what the brake power required is to give the best operation. Then what you have to do is select an engine which will give you that or more power. You select the engine and a rate of and a gearbox to give you the power and the rate of rotation. And then you have to go back and redesign for the particular engine that you've got. So we now know the speed, we know the brake power that we have, and so then we go through through all these calculations here. We can calculate the thrust and hence the pull, and provided that we've got that greater than the resistance that we had as our initial opening gambit, we're okay, we're going to reach the required speed. But if you've simply put the engine in and you want to find out what the best operation is, you can then vary the diameter and the rate of rotation to maximize the pull. So there are various things that you can do. And what we want to do, after we've designed the propeller, we now want to have a look at what happens in the off-design conditions. Now, when we designed the propeller, we usually had a particular power, and it's usually the maximum continuous rating power at an RPM. And that design fixes the diameter, the pitch ratio, the number of blades, and the blade area ratio. And we want to find out what happens at either a different RPM or a different operating speed. For tugs, we typically design at the bollard condition, but then we want to find out what the performance is free running, because quite often a tug contract will be to give you, let's say, 50 tons bollard pull at the bollard, or 50 tons pull at the bollard, with a guaranteed speed of 12 knots when free running. So you design it for the bollard and then check what the operation is going to be at 12 knots. For the trawler, the situation is quite a bit different, in that it depends very much on what the owner wants to do and what is important to the owner. You can design for the trawling condition and then find out the performance free running, or you could design for free running and then find out what the performance is trawling. The other scenario is that you could design for a speed somewhere in between trawling and free running, and then see what the performance is trawling and see what the performance is free running. With high-speed craft and also with large merchant vessels, they typically have a different design condition. They typically design for 85% of their MCR power at the MCR RPM. And then what you want to do is to find out what the performance is at either another power or RPM combination, or even another speed. So we design at the rated power and RPM, and then the off-design condition needs the engine output power over a range of RPM, because what we then have to do in the off-design condition is to match the power demanded by our particular propeller at the off-design condition. And so we need to know a bit about the engine output power curve. Now, I don't know if you can you all read what's on the screen there? This is a typical overall engine power output. This is this is provided by a torque limit up here. This is your 100% power output at the MCR RPM. This is what's called a surge and smoke limit there. This is the lowest RPM that the engine manufacturer wants you to run the engine at in the idle condition. He doesn't like you running it at any lower RPM. And then down the bottom, this is called the low load running limit, because the engine manufacturer doesn't want you to run it down here because you tend to glaze the walls of the cylinders. So this is what the overall condition looks like. Oh, and this is the governor run out curve here, typically from the MCR RPM to what's called the high idle or no load RPM. And typically that's about 10% greater than the, 10% greater than the MCR RPM. So if you, for example, have a diesel engine running at 2000 RPM at the MCR, the high idle RPM will be 2200 RPM. Some engine manufacturers, rather than allowing this governor run out curve down here, they give you a straight line curve at the MCR RPM here. It just depends on the particular engine manufacturer, but most of them will allow you up to a high idle limit up here. Lots of engine manufacturers will give you the just this torque limit curve up here. And so all you'll see on the graph is a torque limit curve up there and a governor run out curve down there. But these are the really important ones and what we need to know, because what we have here is the MCR RPM, and typically that's our design point, or for high speed and other craft, it's down here at the 85% power limit. This is a typical propeller demand curve. And what happens when you go to a lower speed is that this curve shifts off here to the left. I can't see my cursor. Oh, there it is. This curve shifts off to the left, and so it will intersect with this torque limit curve up here somewhere. That's what happens, for example, if you design the propeller for trawling, and then you want to for free running, and then you want to go trawling, the curve shifts off to the left. If you design the propeller for MCR at trawling, and then want to see what the performance is free running, this propeller demand curve will shift across to the right, and of course it will intersect the, I'm losing the cursor again. It will shift across to the right and intersect the governor limit curve somewhere across to the right, and of course at a lower power than at the MCR. This is an engine output curve example from this is a Cummins engine, and you can see the torque limit curve up along the top here, and then a vertical line down there. If you take the data that they give you for this bit up here and then plot it out, you find that it's actually a curve like that. And then going down to the high idle, you get the governor run out curve down there. And so you can get fairly good results from a graph like that, rather than from the one that's actually published by the engine manufacturer. It's worth actually drawing the graph out. So the propeller demand is 2 pi NQ, which we said before, and you can expand that out to 2 pi times KQ times rho n cubed d to the fifth. And for any given propeller at any speed, the KQ is a constant. So the brake power is proportional to the delivered power, and that's proportional to the speed cubed, the rate of rotation cubed. What that means is that if you want to get a 10% increase in power, you only have to increase the revs by about 3%. So that has particular application for tugs, actually, where they often have a 110% power requirement at the bollard. Oh, I've already mentioned this, where if you design for the MCR here and you go to a lower speed, it shifts the propeller demand curve to the left, and you can see the engine output power is less here than it is at the MCR. And then if you go, of course, to a higher speed, when you've designed for this point, it shifts across to the right, and again, it intersects at a lower speed. We said before, tugs are usually designed for the bollard, and we need to have a look at the performance when we're free running. So we plot the propeller demand free running versus the engine output, and that will give us the engine RPM and the brake power. And we then can calculate the KT, typically from the polynomial, gives us the thrust, the pull, and check that that's greater than the actual resistance of the vessel. So this was an example tug that we designed at Commercial Marine Design, a 30 metre azimuthing stern drive tug for 40 tonnes bollard pull, and it needed to have a guaranteed speed of 11.5 knots free running. 2 Daihatsu engines, 1750 feeder Stark at 720 RPM. So that was 1287 kilowatts on each engine. No engine-driven auxiliaries because it wasn't operating in the tropics. No engine-driven auxiliaries at all, no steering pump, no extra alternator, anything like that. The reduction ratio through the azimuthing stern drive was 2.68 to 1. No tropic derate, shaft efficiency 93% because it actually went through 2 universal joints to get up to the stern drive, and then 92% efficiency down through the bevel drives to get to the propeller. At the bollard, we took the tail awake fraction to be 0 and the thrust deduction fraction to be 0.04, resulting in a delivered power of 1101 kilowatts and a torque of 39.14 kilonewton meters. We designed the propeller, and it turned out that the best one was 2.2 meters with a pitch ratio of 0.92, 4 blades, and blade area ratio of 0.668 to prevent cavitation. Now, what that meant was that we had to interpolate between 2 KA series propellers, a 455 and a 470. But we did that and we find that we have a total pull on the bollard of 43.36 tonnes for the 2 propellers operating together. And of course, that's greater than the 40 tonnes bollard pull required. But then we need to check the free running condition at 11.5 knots. And what we do there is actually assume 3 engine RPM. And we knew that the MCR RPM was 720, so we picked that as 1, but then we picked 740 and 760 RPM. So you calculate the brake power demanded by the propeller at 11.5 knots, and you find the brake power demanded is 1355, 1494, 1642, and you plot that against the engine output power curve. And here's the output power curve for a DSM-28 engine. And you can see that you end up with an RPM on the governor runout curve of 741.5 RPM. So what does that do to our result? So we get 741.5 RPM. We calculate the KT as 0.2151, the total pull as 175.8, and the total resistance of the vessel at 11.5 knots, we had as 167.7. So the 11.5 knots is definitely going to be achieved. Now, if you want to know exactly what speed is going to be achieved, you could do it, but you need further information on the resistance versus speed. Speed. What you would have to do is choose 3 separate speeds, starting with 11.5 knots. You'd probably go 11.5, 11.75, and 12 knots. And you would go through that whole process again, and then you would plot the pulls versus the resistance versus speed curve, and where they intersect, that would actually give you the final speed achieved. But because you only need to guarantee a speed of 11.5 knots, and we have our total pull available is greater than the resistance we know for the vessel, we can say, okay, well, it's going to happily reach it. I said on earlier that it's common to specify a bollard pull requirement at 110% power. So I mentioned that you need to increase the RPM by 3% in order to get a 10% increase in power. So it's fairly easy when you're on trials on a tug to have the engine manufacturer's representative lift the governor check to give you that 3% increase in power and run it up to the 10% overload and find out what the bollard pull is, because you've always got a dynamometer on trials on the tug. So for trawlers, we said that the design could be free running or for trawling. And then the off design can then be to confirm the pull available when trawling, or to confirm the free running speed achieved when you go free running if you've designed for the trawling. And again, you just need to plot the propeller demand versus the engine output, and it'll be a similar sort of result to the tug. The example that I've got here is a 23-metre prawn trawler operating in the southeast trawl fishery off the south coast of New South Wales. Caterpillar D353, you probably can't get 353 engines anymore, but it's only a name. 317 kilowatts at 1225 revs. No engine-driven auxiliaries on this one. Reduction ratio of 4:1, much higher than the bevel drives on the tug. No tropic D rate. Gearbox efficiency 97% and shaft efficiency 98%. At 10 knots, we have different tailor wake fraction, typically 0.2, and thrust deduction fraction 0.2, giving you a delivered power of 301 and a torque of 9.4 kilonewton meters. You go through the motions and you design the propeller, and you come up with a diameter of 1.37 meters, a pitch ratio of 1.35, 4 blades, and again, you have to interpolate between the KA 455 and the 470 for 0.687 blade area ratio this time. And you come up with a pull in the design condition of 32.5 kilonewtons. Now that we've designed the propeller for free running, we want to know what the performance is going to be like when we're trawling at 4 knots. So at 4 knots, we pick a tailor wake fraction of 0.15 and a thrust deduction fraction of 0.15. And we assume 3 revs. We know that the MCR RPM was 1225. So here we pick 1200, 1150 and 1100 revs, because we know that a nozzle propeller if you design it for free running and then go trawling, it's going to lose about 5% of the MCR revs. If you take an open water propeller trawling and you've designed it for the free running condition, you're going to lose about 25% of the free running of the MCR RPM. And that is because the nozzle gives you much more even flow of the water through the nozzle itself to the operating plane of the propeller. So these are the ones we picked: 1200, 1150 and 1100. Calculate the brake power demanded by the propeller at 4 knots at those revs and plot that on the engine output power curve. And you can just ignore this curve over here because we've designed for the MCR RPM here, and we're now going trawling. So we've got this demand curve here. And you can see that this intersects the engine output power curve there, the torque limit, at 149 RPM. So then we go back and we calculate the KT, the thrust coefficient, 632, and it gives a pull of 44.5 kilonewtons. Now, for the trawler, we could have designed for 4 knots and then checked on the performance at 10 knots free running, or we could design for a speed in between 4 knots and 10 knots. Let's pick the middle of those for 7 knots and then check the performance both at 4 knots and at 10 knots. And I've put in this table here, which will show you roughly the differences between those 3 sets of conditions. You'll see here that if you design for free running, the free running design will give you the maximum pull when you are free running, 32.5 versus 30.9 and 29.6. If you design it for trawling, then obviously the trawling design is going to give you the maximum pull when you're trawling. So you've got 46.6 versus 45.6 versus 44.5. But if you have a look at this one here where we've designed for 7 knots, it gives you a little bit of both worlds. It's better than the free running design in the trawling condition, and it's better than the trawling design in the free running condition. So it depends very much on what the owner decides is most important for him. For some owners, they want their best performance when they're trawling. Some owners want the best performance when they're steaming or free running. They want to be able to get back home to port and unload the fish as quickly as possible. They don't care so much about the actual pull when they're trawling. But then a compromise design is the design in the middle. It gives you better performance in one area and better performance in another. And then we come to the high speed and the other craft. Typically, these sorts of craft design for 85% of their maximum continuous rating power at the MCR RPM. And that allows them a margin for hull fouling, for sea state, to be able to maintain a scheduled service, for instance. If you want to go the Spirit of Tasmania operation across Bass Strait, for example, they would typically design for 85% maximum continuous rating power, because it gives them that extra 15% to load the engine in high sea states and when the vessel's been quite a time out of dock, because both of those sorts of things provide higher resistance for the vessel. So this shows you what happens on the engine output power curve. I'm losing the cursor. There it is. This is your design point here. This is the maximum continuous rating up here. And you design for here, but it allows you to move your propeller demand curve all the way across to here and still be able to reach the MCR power at a late stage in the docking cycle or in high sea states. Now, I won't go too much into the sort of calculations that you do for those sorts of vessels, because I think we've covered most of the sorts of calculations that you do. But what we're interested in now is how the fouling of the hull and the fouling on the propeller might affect the performance of the propeller. For example, you find that max surf motions provides you with an added resistance in among waves. Different authorities use different percentages of the total resistance added per day. Tony Molland, in his book with Turnock and Hudson, suggests 2 to 3% per month added on the frictional resistance, because most of the hull fouling, for example, adds to the frictional resistance rather than any other sort of resistance on the vessel. Holtrop and Menon, that marvelous series of papers, gave a factor for roughness given by the equation there, the increase in friction coefficient as a function of Ks, which is the whole mean apparent amplitude in micrometers, and depending also on the length of the vessel. You'll see over here, it is actually dependent on length to the 1/3. But once you've calculated the delta CF from these dimensional parameters, the delta CF becomes non-dimensional. And so you can use it with any consistent system of units. And typically the lowest mean apparent amplitude on a new freshly blasted hull, primed and coated, typically is 150 micrometers. This is the sort of effect that you get from fouling and roughness on a hull. And this is taken out of Tony Molland's book. Oh, it was written in 2011, not 2010, as I said earlier. This shows you the timescale in years 2, 4, and 6, and the change in the total resistance coefficient made non-dimensional by the total resistance coefficient itself. Typically, you have the roughness of the hull plateaus out at about a consistent level, but the fouling on the hull grows and grows and grows unless you do something in particular to actually reduce it. And then after you've docked the hull and taken the fouling off, and again it grows like that, dock the hull again, grows like that. And if you shot blast the hull, you get an effect something like this, where you're cleaning the the scale and the general wear and tear off the hull. In the off-design condition, you need the total resistance due to hull fouling, the sea state, and you have two unknowns, the speed and the engine RPM that's going to actually be achieved. So what you do is a bit like the tug and the trawler, where you select 3 RPMs. Here you select 3 separate speeds at and below the design speed. You find the overload RPM and the pull at each of those speeds, and you plot the pulls and the RTF versus the speed of the ship, and the intersection will then give you the speed of the ship that you're actually going to achieve due to hull fouling, sea state, etc. And then you find the overload RPM at this particular speed. The other thing that you can do is find what is going to be the ship speed at an RPM below the maximum. So again, you select 3 speeds, you calculate the pulls at the RPM at each speed, and plot those pulls and the RTF versus the ship speed, and the intersection will give you the speed achieved at those RPM. When you come to fouling of the propeller, as opposed to fouling of the hull, there's lots of interesting work being done in this field at the moment, and in particular at the University of Newcastle in the UK. And they're doing a lot of investigation work about coatings on propellers to improve their long-term performance. The KT and the KQ, of course, depend on the state of the surface, and of course, the smoother it is, the better. As the roughness and the fouling increase, the thrust coefficient goes down and the torque coefficient goes up. And having a coating on the propeller typically maintains the smoothness for longer, particularly if you've got some sort of ablative coating. Or what they call, I think it's called foul release is another word for it. Some of the surface topography that you can get are defined by different methods, shall I say. You have both texture of the surface and amplitude, and they both measure different things. You can see that there's much more waviness in that top diagram there, and more peaks in that lower diagram. So the components are the real surface, which is composed of the roughness, which are the little amplitudes, the waviness, and then the actual form errors. The typical measurements of roughness are what are known firstly as the Rubit surface comparator, and he grades surfaces with the letters A to F. You can have the equivalent height parameter, where RA is the average deviation about a mean line. If you go back to this diagram here, it's the waviness and roughness combined. And then the peak count per unit length, which basically refers to the texture of the roughness. And then there's another one that they call the equivalent sand grain roughness, or HS. And there's a comparison of some of the roughnesses that you get for propeller blades. Okay, oh, have to go back. I somehow jumped to the end there, which I didn't mean to do. This is the modification of the thrust and torque coefficients. The two main ones are due to MOSAD and the International Towing Tank Congress. They have different formulations for the change in the drag coefficient. And we don't need to dwell too much on the actual formulation, because you'll see over here they both give you similar results. But you can see that the KT and the KQ, or the change in KT and KQ, both depend on that value of CD, which we got from there. And as I said, MOSAD and ITTC both give similar results, except that MOSAD includes more about the surface information. Now, many moons ago, I had one of my thesis students do quite a bit of work on the roughness of the hull and the roughness of the propeller. And these are some of his results here, where you can see that if I show on the diagram there, this is the effect on KT, and there seems to be very little effect on KT, but there are much bigger effects on the KQ for roughness on the propeller. If you then have a look here, this is for a vessel that we actually analysed. I don't think I've identified it on there, and I haven't, because I'm not allowed to. You can see what happens here. This is the Rubit B grade of the propeller, and giving you the propeller pull. And this is for the clean hull resistance here, and the vessel was able to achieve 20.99 knots there with clean propeller, clean hull. This one here was with the clean propeller and the hull resistance 1 year out of dock. So it dropped by, looks like 0.33 of a knot. And then if you have a fouled propeller and the fouled hull, it drops down to 20.58 knots. So it was very interesting to see that the if you look at the effect of fouling, if you look at this distance between there and there, it's bigger than this distance between there and there. So the effect of fouling on the hull has a larger effect on the overall performance than fouling on the propeller itself, although they both contribute. Okay. And so then putting all of that together, we found that this was the engine RPM for this particular vessel. And this was the clean prop, clean hull. And then the red one is the fouled prop, fouled hull, and the green one, clean prop, fouled hull. And you can see that the biggest effect was down here at the lower speed than up here at the higher speed end of the deal. Okay, so in conclusion, we've looked at the basics of propeller design, had a look at the characteristics of diesel engines, and we looked at diesel engines in particular because that's what I'm most familiar with, but the principles apply to any of the other sorts of engines. If you've got gas turbines, the same sorts of things apply to gas turbines. If you've got reciprocating steam engines, which we actually did one of, actually, when we did the restoration of the steam yacht Ina back in the mid-1980s, we had a new reciprocating steam engine in her, and we fitted a Gorn series propeller to her, and she achieved the speed on trials. And I have to say that one of my abiding memories is doing trials on Sydney Harbour. They had a measured distance upstream of the harbour bridge at that stage. I don't know if it's still there anymore, but you could talk on the deck of Ina at full speed, just as we're talking now. Whereas if you were working on the back deck of a trawler with a screaming GM in it, you'd be having to shout at each other to actually make yourself heard. I have an abiding affection for reciprocating steam engines because they're so quiet. We had a look at the off-design performance of 3 different types of vessels. We had a look at the effects of roughness and fouling of the hull, and the effects of roughness and fouling of the propeller, and then finally on the combined effects.